Thanks everybody for coming. Thanks Morgan for agreeing to meet with us today. This is Dr. Morgan Gorris. She is a postdoctoral fellow at the Los Alamos National Lab. She's a director's postdoc fellow. She got her PhD in Earth System Science in 2019 from the University of California, Irvine. Her master's also at Irvine in 2016. Her bachelor in Earth System Science and Engineering at the University of Michigan in 2014. She's done some really awesome work since part of her PhD, but also progressing on into her postdoc at Los Alamos, working on the sort of the nexus of human health interactions with climate, with a focus on a variety of different infectious diseases. I think we're going to hear mostly about West Nile today, but also she's got a lot of her work, particularly during her PhD, was focused on the spread and predictability of valley fever. And then I also noticed, which I didn't know about until I saw her CV recently, that she's done a lot of work recently on COVID-19 as well, for which she actually received a couple of awards through LANL, the Postdoctoral Distinguished Performance Award, and also a SPOT Award, which I'm not exactly sure what that is, but sounds awesome. So yeah, we're really excited for Morgan to join us. I'm hoping that this can represent sort of a shift in our focus as a panel, to begin thinking about this nexus of human health and climate change and variability, and how we sort of ingest, or how different sectors of industry sort of ingest climate information to make decisions. So with that, happy to pass it along. Thanks, Morgan.
Thanks, Dylan. I appreciate the introduction. Today, I'm going to talk about projecting the risk of environmental infectious diseases in response to climate change. This is something that, like Dylan said, I got really interested in during my PhD. Basically, how can we take, climate data and weather data and understand how those two things affect infectious disease dynamics, like where diseases are, how many cases we have, and then how those things might shift in response to climate change. And so that's what drives a lot of my work. And we know that human health is already suffering from climate change, even more so than just changes in infectious disease dynamics. So climate drivers can cause different exposure pathways for human health, like increasing temperatures, precipitation extremes, extreme weather events, and sea level rise can cause people to experience extreme heat, like heat waves, reduced water and food security, displaced populations. Soon there could very well be places on Earth just that aren't habitable based on extreme heat. And what I got really involved in, which is changes in infectious disease agents. And so we're seeing a lot of these exposure pathways highlighted in the news. For example, in the New York Times, they've covered on many different heat waves over recent years. We know that pollution is being made worse by climate change and can accelerate certain diseases, especially lung diseases. And this kind of opens a rabbit hole of environmental justice issues as well. And then there's this last title down here: Lyme disease reaches a new normal in the Finger Lakes region of New York, where the ticks that carry Lyme disease have started spreading north, and they saw like a 3,000% increase in the number of reported cases in 2019. So this is, not something that's new per se. We know that climate change is going to affect human health. The first climate assessment report had a section for human health in it. It was 6 pages long. Fast forward to the 4th National Climate Assessment, there's a whole chapter on human health, highlighting things like heat waves, infectious disease dynamics, mental health issues that will be caused by climate change or exacerbated by climate change. And the first line of the keynote box in the human health section is climate change affects the health of all Americans. And I think that's really the best way to summarize it. So my work really lies at the nexus of humans, health, and the Earth system. And the term that some of us use to describe these connections is geohealth. And this term has since been taken up and highlighted by the American Geophysical Union community. And so my work lies at this nexus of geohealth, where humans living on our planet, we are exposed to different environmental conditions that can affect our health, and all these things are very highly interconnected. There are a lot of organizations that study these interconnections in some way or another. So at the AGU meeting, there's a whole new section that was developed 3 years ago called Geohealth. At the AMS meeting, there's a whole section that's been around for, I think, almost maybe 15 years now called Environment and Health. The Department of Energy and Department of Defense are obviously very interested in health-related issues because they are a direct threat to national security. The EPA and CDC both have programs and a group of folks that look at health-related impacts. The NIH has the National Institute of Environmental Health Sciences, and the World Health Organization and World Meteorological Organization a lot of times work together on different climate and weather and human health impacts. So in terms of infectious diseases themselves, we know that rising temperatures and shifts in precipitation could reshape where infectious agents live. And with that, it can reshape where diseases are. So I am typically residing at the yellow dot there in Los Alamos, New Mexico. And let's say we have this mosquito species that lives south of this within the green bounds, mostly throughout Mexico. Well, if temperatures rise, that could cause the mosquito to potentially move further north because now the habitats north have warmed and are now suitable for this mosquito to live. But maybe also down south, it's now too hot for the mosquito, so that boundary might lift north as well. Okay, so now we have a new bound for this mosquito, but let's say it's a dry mosquito and it doesn't want to live in the wet eastern part of the United States. Well, maybe our new distribution for this mosquito species is across the southwestern US. So where I was once sitting, I may not have been at risk for contracting this mosquito-borne disease. But now, with this change in habitat suitability, new communities are at risk for contracting this mosquito-borne disease. So these changes in temperatures and precipitation, as well as other environmental variables, are going to shift where diseases are, not only in the US, across the world. So a lot of what happens when we go to study these dynamics is that we're dealing with two different issues. We're dealing with, one, how do we actually model the disease? How can we understand where the disease is, how many cases of the disease there will be? And then two, how do we forecast what will happen in the future? So not only are we going to have uncertainty rolled into our disease model, we also have this uncertainty kind of rolled into our climate projections, or our shorter term climate projections, and even our weather projections. So that's where a lot of the difficulties come from when we start studying environmental infectious diseases, as kind of coupling two different forecast uncertainties together. And that's something that I think would be beneficial for maybe this group at large to think about. But really the objectives when we go to study some disease is, one, we need to model the disease based on climate conditions, if the disease is, affected by the environment. And then two, apply climate change projections or whatever, forecast period you're looking at onto the disease model to understand how the disease dynamics may respond. So for the purposes of my research, I look at non-communicable diseases. Those are diseases that are not spread from person to person when I study climate and disease relations. So the COVID stuff I did had nothing to do with weather. But all the other disease systems that I look at are diseases that have vectors or have some component that is responsive to surrounding environmental conditions. So I call those environmental infectious diseases. So I'm going to focus on one of the projects I've been working on, just to kind of highlight one of the processes of hopefully meeting these objectives, and that's looking at a disease called West Nile virus, which is a mosquito-borne disease. So for this project, I was interested in understanding what climate conditions structure the spatial extent of West Nile virus in the United States. And can we create a model that helps describe this extent based on climate conditions? And then second, how might the spatial extent of West Nile virus shift in response to climate change? So West Nile virus is the largest cause of mosquito-borne illness in humans in the United States. It was first introduced to the US in 1999 in New York. And then each year after that, it started spreading further and further west. By 2005, we had cases all across the contiguous United States. On the top is a map of the mean annual cases, average from 2005 to 2018. Really what you're looking at here is population hotspots. Where we have more people, we have more cases. On the bottom here is a map of disease incidence. So this is taking the number of cases and we normalize by the number of people living in each county. So it's just cases per 100,000 population. And you can see a clear structure comes out of looking at the disease incidence map, where the highest levels of disease incidence are in the north central Great Plains. It kind of makes this V structure stretching down throughout the Great Plains. And then we have additional hot spots along the Columbia Plateau and in southern Idaho area, and also kind of a little tongue of moderate incidence that stretches into the southern Mississippi Valley area. And then when people get West Nile virus, they get it by being bit by an infected mosquito. Only about 25% of people have symptoms that range from flu-like. You could get sick and not really know you have West Nile virus and get better in a week. And you'll have, typical flu symptoms. But a small percentage of cases do develop into a serious form of the disease called neuroinvasive. That's where it can affect your brain, and it can be fatal if left untreated or in severe circumstances. So the primary transmission cycle for West Nile virus is between birds, which are the viral host. That's where the virus, is dormant and lives. And then mosquitoes will bite the infected bird and they will carry the virus around. And then humans can become sick when they're bit by an infected mosquito. But we're actually considered a dead end host where we don't make enough virus in our blood for the disease to then be spread outside of us. So understanding this transmission cycle dynamic for each disease you study is really kind of the baseline knowledge that you need if you want to try to understand how climate conditions could be affecting the disease, because you need to really understand what part of this transmission cycle could be affected by climate or weather conditions. For West Nile, every part can be affected by climate conditions. Temperatures affect how fast mosquitoes breed and how quick their life cycle is. It also affects the timing of bird migration, north and south, in and out of the United States. Mosquitoes need water for their breeding habitat. Birds need water for their habitat. And then a little bit more nuanced, but people do respond to climate conditions as well. If you have a, really hot summer, maybe more people are likely to spend it indoors. Or maybe more people are likely to be outdoors at night when it's cooler, and that's when certain mosquitoes tend to bite. So climate can really affect all parts of this transmission cycle. And many studies have tried to, or I shouldn't say tried to, but many studies have broken apart this transmission cycle to understand how it could impact each facet of this. So how higher temperatures affect the mosquitoes, and if you can see it, in West Nile transmission. But what I do here is I kind of take human cases as a proxy for all of these relationships. So I look at climate conditions and then how it might affect the number of human cases, since that's something that if we have a prediction for, we can make health decisions based on it. So if there's a year with particularly high risk or high number of cases predicted for West Nile virus, then we can allocate, human and health resources appropriately. On the top is a plot of the number of West Nile cases per year. It varied quite a bit before this 2005 period as the disease spread west. And then we kind of had a lull in the 2009 to 2011 time period. There was a big outbreak in Texas in 2012 that really drove up the numbers. And then it's been a little mostly steady since then. So the data that I used to study West Nile virus was human case data from the CDC. I have case data from 2005 to 2018 available at the county level by year. And then again, I calculate disease incidence so that we're not just looking for human population signals, but we can actually get a measure of the number of cases normalized by population and compare large population counties with small population counties. The climate data that I used for this study was from the PRISM product from Oregon State. And then I also used the bias-corrected spatially downscaled CMIP5 data, looking at mean annual temperature and total or cumulative precipitation annually. And so this data was all available at a 4-kilometer square grid, which was suitable for analysis at the county level. And I aggregated the data into the meteorological seasons, where DJF was winter, March, April, May was spring, etc., to compare seasonal climate conditions with West Nile virus disease incidence. And so, as with all science, you start with, an exploratory analysis of, Okay, well, do we see any signal in the noise here? Do we see any relationships between climate conditions and levels of disease? And so one of the first things that I did was look at scatter graphs of levels of seasonal precipitation and temperature, which I'll show on the next slide, and levels of West Nile virus incidence. So this is total winter precipitation along the x-axis here on the left, and then West Nile virus incidence, so cases per 100,000 population. And each dot here represents one of the 3,100 counties in the United States, and this data is, averaged over 2005 to 2018. And then on the right-hand side, I did the same thing for summer precipitation levels. And one of the first things I noticed was that there's kind of these thresholds for increased levels of West Nile incidence. So for winter precipitation, it seems like a county has to have really low levels of winter precipitation to have higher levels of West Nile virus incidence. And then in summer, there almost seems to be this threshold too, where, any county that had higher than like 125 millimeters per month of precipitation really had lower risk of West Nile virus, but below that, the county had higher levels of West Nile virus incidence. And so there seemed to be, these clear boundaries for increased West Nile virus. And when I looked at temperature, instead of boundaries, I found that there are kind of temperature optimums for increased levels of West Nile. So there's this, curve here where winter temperatures are on the left and summer temperatures are on the right. And if winter temperatures were, just slightly below 0 degrees Celsius, there was higher levels of West Nile virus incidence, kind of tapered off in both directions. And then there was also this, summer temperature optimum for increased West Nile incidence. So for this application, these thresholds and optimums made me think that some type of machine learning algorithm would be best for pulling out these relationships between climate variables and West Nile incidence. And so what we did was use a machine learning algorithm called a random forest model to recreate the spatial structure of West Nile virus incidence across the United States. And so with this model, I input the 8 seasonal climate variables. So we've got temperature and precipitation for all 4 seasons. And then it was predicting on the county level mean annual West Nile virus incidence. And so we ran this, several different times. We used bootstrapping, resampling technique, created 10 bootstrap models. For each run, we used 1,000 trees, and we used 70% of our counties to train the model, and then 30% to test the model performance. And so on the top here is our modeled mean annual West Nile virus incidence, and on the bottom, for comparison, is our observed West Nile virus incidence. And so our model does an okay job of capturing that V-shaped structure of higher incidence throughout the Great Plains. It also captures some of the higher moderate levels of incidence in that southern Mississippi Valley area. But overall, it gives us an okay baseline of a risk assessment of where West Nile virus incidence could be higher just on the basis of climate conditions. So I just said that, so I'm going to keep going. One thing that the random forest model allows us to do is kind of break apart some of the relationships between like those cutoffs that we were looking at in the scatter graphs, we can actually look at what's happening in our random forest model. So for example, in the top is a map of one of the winter precipitation cutoff. So it basically said if you had less than about 22 millimeters per month of precipitation, you're going to be put in one category, which was a higher risk category for West Nile virus, or higher incidence category for West Nile virus. And then if you had greater than 22 millimeters per month of precipitation, you were categorized into a lower level of West Nile virus incidence. So winter precipitation here is really the giveaway for that V-shaped structure of higher West Nile incidence across the United States. Whereas on the bottom, this is a map of the cutoffs for winter temperature, where the highest, the warmest winter temperatures, which are in the darkest red across the south, had the lowest levels of incidence, and then moving up north to the lighter colors, which were the colder winter temperatures that had the greatest levels of incidence. So combined, the dry, cold winters ended up coming out as kind of the most important predictive factors for structuring the West Nile virus risk across the United States. The other two factors that helped in the model ended up being fall precipitation and summer temperature.
Morgan.
So yeah.
Sorry, just a quick clarification question. Could you just go back to that table, please?
Yeah, absolutely.
You might have said, and I just missed it, but the column on the far right is percent decrease in mean squared error between the obs and the model.
Sorry, so this is a way to basically get variable importance out for a random forest model. And what it does is it randomly permutes the county, so let's say for the top one, winter precipitation, it will randomly scramble the winter precipitation values for the counties, rerun the model, and calculate how much worse the model performs. So it, based off of mean squared error. So it calculates the normal model, and then it will randomly scramble that variable to see how worse the model performs. And that's how we get variable importance out of a random forest model.
Okay, so the higher the number here, yeah, so the higher the number here, the more important it is to the model.
Yes, the higher the number here, the more important it is to the model, because when we randomly scrambled that model, or that variable, the model did worse.
Gotcha. Okay, thank you.
Yes.
Could I, this is Matt, could I just follow up on that, so I can be clear on this? So are these differences significant? I mean, the fact that you go 20 to 15, is that really, should we take that as 20 is really a more important variable than 15? Or, is that tolerance like within 20 or 30%, and then we should view these as all equal?
You can take these as face value. So they are, I wouldn't say they're in like a certain tolerance band.
You don't know me, or you'd never say face value to me.
Okay.
No,
okay. Take it back. So you can view these as relative to one another, so that we can make the statement that winter precipitation was a more important predictor of the structure of incidence than winter temperature. So I don't think they like, yeah, there's no like band to really analyze them within. Does that make sense?
Well, I mean, there's got to be some uncertainty, right? You have sampling issues. I'm just trying to get a sense of how to interpret these, I guess.
Right. I would interpret them as relative to each other, but not comparable to other systems. So if you were to create a West Nile virus model based on like land cover classes, and you had a % decrease in MSC in that model, like you can't compare them across modeling systems, but to compare the relative importance within the same model would be most fair. Okay, I'm going to keep going because I know I'm pushing my time a little bit already. Okay, so then there's always a trade-off between, creating a explanatory model of a system and creating a predictive model of a system, where you can create a very good predictive model and have no idea what's really driving that predictive model in terms of, what your coefficients are doing, et cetera. Or you can create an explanatory model where you are using predictors that you know should have, an impact on your system, but may have less predictive power for whatever reason. And so this is always a trade-off when it comes to, any modeling, and especially disease modeling. So I tend to stay on the side of explanatory models where we can actually understand the mechanism behind some of our predictions. And so what's likely happening here with our model is that it's describing the ecological niche of a certain mosquito species that is known to be a good spreader of West Nile virus. So Culex mosquitoes is a genus of mosquitoes that are known to be species that both bite birds and bite humans. And so that can be a bridge vector from the host to us and create more disease cases. And so a lot of these Culex mosquitoes are associated with agricultural areas. So it's kind of wasn't a surprise that this popped up as, the Great Plains area, and that ultimately this could be describing where the vector is living. So the next step was, since we have this modeling system set up to recreate the spatial structure of West Nile virus, then we could use projections of climate to understand how that risk may shift in the future. So from the BCSD data set, I grabbed the climate data from the 30 different Earth system models, looking at climate change projections for both mean annual temperature and precipitation across the United States. And then for the purposes of this presentation, I'm just showing the RCP 8.5 scenario. And so temperatures are expected to increase 3 to 6 degrees Celsius, and precipitation might decrease across the southwestern United States, where we had a little bit of risk of West Nile virus, but there might be little change throughout the Great Plains. So when I take these climate projections and put them into the random forest model, I get an estimate of how disease incidence might shift in the future. And so our model that started out predicting, the highest levels of West Nile virus in the Great Plains and Northern Great Plains, that V-shaped structure actually starts moving north outside of the United States into Canada. And so the highest levels of risk might actually leave the United States. The moderate levels of West Nile virus incidence, like this one patch in the southern Mississippi Valley area, also start to travel further north in response to the warming temperatures. And so these moderate levels of incidence start to travel into more highly populated areas. So although the highest risk or highest incidence for West Nile might leave the United States, when I actually back out how many cases this incidence translates to, there might be more cases of West Nile virus overall. So plotted here is time throughout to the end of 2100, and then the number of West Nile virus cases per year on the y-axis. RCP 8.5 is in the orange with the diamonds and the higher number of cases per year, and RCP 4.5 is the green with the circles on the bottom here. So although that V-shaped area of highest incidence might move north, those moderate levels of incidence might also shift north and cause more cases overall per year. So some of the main challenges to studying these systems, to summarize, what people and looking at climate and infectious disease deal with, I think, would be good for this group to consider. Problem number 0 is something that I don't think you all can help with, but it's access to the epidemiologic data. It is very hard for people to get their hands on case data because there's a lot of, data sharing policies. So that's kind of just an aside to if and when you start studying human health. But one of the main challenges for people who do not have a background in weather and climate is access to climate data. Usually it comes in, net CDF files or some obscure file format that a lot of health specialists or other, physicians or health related people have never had exposure to. So just knowing where to get the data, how to access the data, and literally what to do with that data file is a huge stepping stone and limiting a lot of epidemiologists in studying, climate and human health relationships. Another main challenge in studying human health is combining the climate and disease forecast uncertainty, which is something that right now I've kind of written off as, okay, at some point we just gotta, make our best estimate and either look at the disease forecast uncertainty and kind of take the climate, as more, this is what's going to happen, or take the climate or take the disease projection as this is what will happen with the disease, and then we can look at the climate uncertainty. But for better or worse, when you start combining the two, you almost render your forecasts and projections as a shot in the dark, just a complete guess, because there's so much uncertainty. So that's something that's quite challenging to deal with. The third problem is access to subseasonal and seasonal climate forecasts. So a lot of health decisions, there's a certain time frame that health decisions are made. In terms of mosquito-borne diseases, some of those decisions could be mosquito abatement. So they will go and spray adulticide, or they will put larvicide in an area, and they have to make those decisions at least 3, 4, 6 months in advance so that they can acquire the chemicals, acquire the equipment, and make plans to spray. And so I've found that while weather predictions and infectious diseases do have their own category, and projections of diseases are also helpful, we really need something to fill in the gap between the two. We would really benefit from a solid subseasonal to seasonal climate forecast in the health world. And so I wanted to end on the main challenges here today to hopefully open it up for discussion. But thank you for taking the time to listen to an introduction to health and climate and West Nile virus.
Great. Thank you so much, Morgan. So we'll take about the next 17 minutes for questions from her. If you have a question, you can use the raise your hand button or you can type it into the chat box.
I don't know how to raise my hand, but I'll just jump in. There we go. I got it raised. Anyway, first of all, thanks, Morgan. This was perfect. This is exactly what I was hoping you would present. I love this main challenges slide. I took a screenshot of it because I think this is exactly the information that the panel needs to begin thinking about how to like apply, right, exactly these issues, apply our knowledge of the climate data and our forecasting capabilities in a useful way. So one question I have for you real quick is I was struck by that animation of the redistribution of incidence cases as a function of time in using the climate model projections. And it reminded me of a method that people use in econometrics, looking at the impact of climate change on socioeconomic output, where I forget the exact phrase for it, the jargon for it, but basically what they do is they take a year of data that they think looks like the future. They think that it looks like the year 2100, whether it's like an El Nino year or particularly just some random interannual year where it looks like the future, and then they see how the system responds to that perturbation on a year-to-year time basis and use it as sort of a test to test a litmus test to test their projection to see how well their projection might be looking like the real world. So I'm just wondering if that is a tool that people use as well, and is that something that you could use? I understand that your epidemiological data is relatively limited, but going only back to 2002. But I mean, could you pick an El Nino year out that has some spatial distribution of precip and temperature that looks similar to 2100 and see if mosquitoes are really responding in that way, for example?
That's a good question. And as far as I know, I don't think I've seen any examples of someone using that method. Something that is a little tricky with that method is that when you have a outbreak of a disease in a particular area, that population then typically develops immunity. And so something that would be challenging for that method is taking into account the level of human immunity. And so I'm thinking with West Nile, when I mentioned in 2012, there was a large outbreak in Texas that year. We would kind of guess that Texas would have lower cases in following years, even if they did have the same climate conditions, because your population kind of already got slammed, and then there wasn't enough, turnaround time of the population for them to be susceptible again. So I think you could try. I haven't seen it, but one thing would be considering how to account for the human population dynamics. You would have to make some assumptions about having a naive community for the disease, or having a turnover with your community, if you will.
Right. That's a good point. Thank you.
All right, I see John Nielsen Gammon, you have your hand raised.
Hi. Yeah, thank you. Nice talk. Thinking about the importance of, say, wintertime precipitation, and you've got county scale epidemiological data, but county scale climate data is, presumably you're taking averages over the county, but you've got, in much of the West, you've got the precipitation falling in the mountains and the people living in the flatlands. Have you tried to deal with that issue in any way?
Yes, this is a really good point, and something that is unfortunately quite tricky when it comes to connecting climate and epidemiologic data. So some studies, when they look at a like highly focused area, like say California Central Valley, where a lot of the times those huge counties, you have like the Sierras on one side and you have like Bakersfield on the other side. What they do is they will look at weather station data instead of some type of gridded climate product. For better or worse, you're trading one set of issues for another. Some idea that we had kind of tossed up, but I have not personally explored, is trying to like weight the climate data by our population data set. So you would almost, if you had, you know, Bakersfield that had more or less rain, and the Sierras that had, you know, nobody living there and had more rain, you would do a weighted average of the precipitation data across that county. I have not personally done that yet. We've chatted about it. I don't know of anybody who's tried that. But otherwise, I've kind of just taken it as it is, and but you're absolutely right. There are just some, especially in the West, there are just counties where people aren't living in half of it. So it would be very interesting to hear if anybody has any other ideas for, yeah, kind of spatially biasing the climate data.
Yeah, population weighting could work in two ways. You could have gridded population data, or you could basically just use the elevation of communities and do population based on that, or alternatively, do things based upon elevation in the sense of saying, okay, well, let's take the lowest 50% of elevation levels and use that data, so that's where most of the people are going to be. So those are possibilities.
Mm-hmm. Mm-hmm.
Thanks.
Thank you.
All right, a question from Matt Newman.
Yeah. Let's see. Okay. Sorry. Yeah. So I wanted to get back a little bit to this issue of uncertainty, because I think this is, to be blunt about it, the reason why I tend to discount almost all of this sort of work. Because I don't think you have any sorts of uncertainty estimates here, and you're training on very short periods of data. So you have 13 years of data, you're getting a precipitation temperature relationship, which looks a lot like geography. So for all you know, you're really picking out geography. It's possible there's a very little climate signal here at all. And if the, you know, for example, maybe it has more to do with soil type, or the fact that you've got aquifers in some areas and not in others. You know, what is the nature of the species adjustment to the different, you know, the mosquito species and the bird species adjustment to the different vegetation, which may or may not change with climate change. There's a whole host of elements that are very hard, I suspect, to pull out. And as Dylan rightly pointed out, this has to me always been an issue with a lot of these kind of analyses as well. You typically train on the entire period of time. You don't have any relationship between in terms of variability. So if this 13 years happen to be particularly skewed by a La Nina or El Nino mean, or you just happen to have, let's say, drought in the West for some period of time, or you had some just random element to the climate, you may be artificially picking that up as well. So having some idea of the uncertainty of your relationship to the climatological variables seems to be really important, because then you do a projection where you have zero uncertainty in the projection, right? My understanding of that CMIP5 environmental variable, or whatever, I forget what they're called, but that database is that it's one of the models. It's not an ensemble. It's not even a spread across models. If you were to do the same sort of thing with, let's say, a large ensemble out of one model where you have 40 realizations, you know, of the next 70 years, you might get a very different picture depending upon which realization you pulled out. And that sense of uncertainty could be so large as to swamp any signal. I mean, I have no idea. Maybe it doesn't. Maybe the sense of the uncertainty is really small, but there's no way to tell. Because there's no way to tell it, it's just really unclear to me how to treat this. How seriously should I look at this? The time scales have got to be coming into play too, especially if you're talking about species adaptation. It's a different thing to make a prediction for species, I suspect, over the course of a season, as opposed to a year or a decade or a century as well. And I don't get the sense that there's any of that information here. So it's really hard. It's just really hard for me to know even where to begin in terms of trying to relate this to kind of our general understanding of the climate system. I mean, is there any focus in the future in terms of trying to get at some of these uncertainty estimates?
Yeah, so something that I haven't done yet for this problem, but have looked at for valley fever, the infectious fungal disease, is break apart the projection, like use the same disease model on each of the ESMs. So here, what I showed today, I was averaging the output from the 30 ESMs together, and I did not run them each separately yet. But one thing that I did for the kind of valley fever project, which is, different model, same kind of idea here, is take the disease model, run it for each of the ESMs separately, and then I created a map of like model agreement to see the goal for that study was what counties might be endemic for the disease in the future. And with the 30 different ESMs, I then created like, okay, 25% say this one might be endemic in the future. 100% agreed that based on climate conditions, this might be endemic in the future. So at least it took the disease model as truth here, but showed the uncertainty in the climate projections. So that decision makers could then look and say, okay, well, we're on the fringe of this disease maybe being endemic by 2070. So like, we don't have to, act on it by, in the next 10 years.
It's not just the uncertainty between models. It's just the underlying climate uncertainty. There's a lot of internal variability in the system, and for some variables, it can take a very long time before you could pull out the trend. For precipitation, in pretty much every model, you're looking at something over 50 years. For something like soil moisture, you might not be able to determine the trend by the end of the century in some areas. I mean, there's that level of variability because the timescales are a lot slower. And so I think that it's that nature of the uncertainty due to the internal variability relative to the trend, which I think is relevant, because I can't believe that the pathwise evolution of the climate system has zero impact on the species development, right? If it was abnormally wet for 30 years before you eventually got a dry trend, that should have a different impact than if you start out dry and then had a short wet period and then went back to dry. I mean, some of these things must have an impact, I would think.
Yeah. And I think that we just can't pick some of that out yet.
I'm gonna push back a
Yeah.
little bit on that comment because the role of natural variability applies whether or not there's climate change. You can do the analysis of the climate change component with the ensemble of models, and that tells you something about climate change component. And whether or not something's affected by climate change, the natural variability part of dealing with what's going to happen in the future is always going to be there.
Yeah, I think what I'm kind of curious about is how much the pathways dependence matters, though. That I think is the issue when you're talking about species, is that you can't, if you're just thinking about variability and say, well, what's the weather, what's the climate going to be in the year 2100? Maybe for a lot of variables you could average out. Now, not all of them. That's That's one of the things, even in the CSM, it's somewhat surprising along those ways. But even apart from that, there's this issue of, when you're making these projections, you have to pick a date. Say, well, we're going to see a change by 2050 and 2080, 2100. These lines look so certain. You get up there and say, this is what West Nile virus is going to do, and it looks like And the fact is the amount of uncertainty, and like you say yourself, you haven't even added in the disease, the uncertainty you have in terms of how the disease spreads. I find it, I mean, I understand why you want to do these things, but I don't understand how you can feel that you have confidence in any of these projections. And that to me is what whenever I see this stuff, I think, man, I understand how important this is. But importance doesn't mean we have an answer. It just means it's important. We need to keep working on it. I completely agree with that. But
So we're running out of time here. Maybe we should let Hyann ask her question real quick.
I have a quick question, Morgan. This is a very interesting talk, and I wonder whether there is any operational, like say CDC is working on an operational forecast for, say, West Nile disease, and or who is doing this kind of operational forecast? Because for weather forecast, like climate prediction, we have research prediction versus operational, and I just wonder who is doing operational forecasts and whether there are any conversations between CDC and state climatologists to discuss how to use our climate prediction information to provide these disease forecasts.
That's a great question. And I guess you just highlighted like my career goal that I hope we can get to, because I think there's a huge need for this. Because I'm really not aware of an environmental infectious disease prediction system that the CDC uses yet. There have been some forecast competitions. Like this past year, they put out a call for West Nile virus forecast competition where many agencies put in a prediction of how many cases we would have in 2020. And so I think it's something that the CDC is starting to explore and put more resources into, but not something that they have the infrastructure for. I will say that they, obviously there's an increased interest in this because of COVID, and they do have a flu forecasting model that I don't think many groups incorporate climate conditions into, but they have at least a flu forecasting system that they're using. So hopefully we can expand this to other environmental infectious diseases.
Thank you.
Yeah, good question. Thanks.
All right, I think we'll wrap up today's webinar. So thank you so much, Morgan, for taking the time and giving us the time to present to the panel. So thank you everyone for joining.